Hello and welcome. In this worked example, we've got a slice of germanium. And this particular slice of germanium has a cross-sectional area of 1 square centimeter, and it carries a current of 56 microamps. As I read through the question, I can kind of see what my work is going to be. This micro is probably no good, and I'll need to convert that. If I look at the square centimeters, maybe your instinct is to say, well, I want to convert that into square meters or something. But 1 is such a nice number that if I can avoid, like if I can work with this number, I kind of want to. It gives the number density of the charge carriers in this germanium. They give you a nice little picture down here too. So there's the number density, but look, it's in cubic centimeters or per cubic centimeters, right? So this is the number of electrons that's in each cubic centimeter, of this germanium. And so the units here already agree. Maybe we could sort of avoid the conversions to like converting this into cubic meters, for example. It says each charge carrier has a charge equal to the charge on an electron. And I know that electrons have a charge of 1.6 by 10 to the negative 19 coulombs. And that's a value that you should have recorded and probably committed to memory by now. That's the charge on an electron. It's a really important number. You're lucky enough that you live in a time when we know this. We've quantified charge and we know its value. Most human beings throughout history did not know this, right? Obviously. And even the people that really studied it, that wanted to know it, like Kirchhoff, somebody that would have been very interested in that answer, never knew it. Because he studied it before we did the experiments. So that's cool that we stand on the shoulders of giants. All right, average drift velocity, you may recall, is shows up in an equation for current. So current in general is charge per time. But we derive an equation, which you can click on the link above if you want to see the derivation of this equation. But it's I equals NAVE, and that V there is the average drift velocity. If you have worked through the ACE physics syllabus, then you know that one of the learning objectives is to make reasonable estimates. And if you just consider these answer choices and notice that they're off by orders of 10, only one of these is a reasonable drift velocity, and it is choice A. You could avoid any calculation and just say, well, 0.1A, that's the only sort of sensible speed. Everything else is way too fast. But let's prove it with a calculation here. So let's make V the subject of this. So V would be the current over NAE. And because the number density is in per cubic centimeters and the cross-sectional area is in square centimeters, I kind of want to leave it in those units as I substitute it in, just keep track of them. What's going to end up happening is that my final answer is going to be in centimeters per second. And then I'll convert that because I only have to convert sort of the linear centimeters to meters. Here, remember, you have to keep in mind, how do I convert square units? How do I convert cubic units? And it's just, converting it as many times, right? Like you've got to divide this by 100 and then 100 again to get it into square meters, right? You can't just divide this by 100. That does not convert this into square meters. You got to take care of each one of the units. So watch as I make these substitutions. So I'm using this equation here. So the numerator is the current I, and I'll take care of this 56 micro is just 10 to the negative 6. And so my advice is when and where you can, just substitute the metric prefixes for the order of 10 that they stand for. I'm going to remind myself with this equation over here that an amp of intensity of current is equal to a coulomb per second, right? So a coulomb of charge per second of time. So that's really what an amp is. So 56 microamps is 56 micro coulombs per second. I'm going to keep track of the units. Okay, so that's my numerator. The number density is this value right here. So it's 2 by 10 to the 13, and it's really electrons per cubic centimeter. So it's like electrons, and I'll put the per cubic centimeters back up here in the numerator rather than writing a new denominator. So that's N. A is the cross-sectional area, and again, it's like this number here, 1, is so friendly that kind of want to keep it in our calculation if we can. So 1 centimeter squared. And this is why we left it so that, 2 of those are going to cancel those 2. And I'm just left with centimeters per second. Those are going to be my units of velocity, right? The only thing I haven't substituted in was E. E is elementary charge. It's this number. And see how coulombs are going to neatly cancel out those coulombs. So the units always sort of work out to give you sensible things like centimeters per second of velocity, right? And so the final step here is going to be to just convert those centimeters to meters divide by 100 one more time. And this is what I mean. You only have to divide by 100 to convert this linear centimeter per second to meters per second. You don't have to divide by 100 twice. Let me just sort of show that real quick. So if an area is 1 centimeter squared, we have to convert that like 100 centimeters per meter, 100 centimeters per meter. So to get sort of meters squared, we're dividing by 100 and then 100 again. We're dividing by what? 10,000. Dividing by 10,000. All right, so if you type all that in the calculator, it ends up 17.5 centimeters per second. So dividing by 100, you get 0.175 meters per second. And indeed, you know, choice A is the reasonable one there, and it's the correct answer to this question. This has been another worked example with Dr. Schleif. Still living the physics life. See you next time.